Greetings everyone. Welcome to tinyML talk series. Today we have these two interesting topics for the talk. My name is Rajen Bhatt. I am Director of Machine Learning Division in Queexo, and I will be moderating the talk series today. Before we begin our talk, I would like to thank tinyML talk sponsors, Deep Light, Edge Impulse, Maxim Integrated, Queexo, Reality AI, and SynSense. If there is an interest in the sponsorship for the tinyML talks, please contact Barry at tinyML. Here is the schedule for next tinyML talks. We have Michael Gelda from Ant Micro will present TensorFlow Lite microcontroller on Renault platform, and we will have Stuart Pfeffer, CEO from Reality AI. He would be presenting building products using Edge AI on microcontrollers. Please contact Talks at tinyML if there is an interest in presentation in this tinyML talk series. Okay, so here is our first talk. Our first presenter today is Hiroshi Doyu from Ericsson Research, and he will be presenting tinyML as a service, which basically discusses about bringing machine learning inference to the deepest IoT edge. Hiroshi's introduction. Hiroshi Doyu is having more than 20 years of experience as a system software developer, researcher, and he is also a long-time kernel contributor. Hiroshi is part of the Ericsson Research IoT technologies team. Hiroshi, to you.
Today, I'm going to talk about our project, tinyML as a service. This is about how to democratize tinyML to the every corner of business cases. So here's the agenda. Briefly introduce about who I am, then our perception of tinyML, then our proposal, tinyML as a service. Then I'm explaining about why ecosystem matters. And at last, briefly talk about the ongoing then with some device. So, who am I? I'm a researcher in Ericsson, Finland, and recently I'm so interested in embedded AI. And last year, I presented some talk about the learning unikernel on learning tinyML on unikernel with a functional programming language. It was in Embedded Linux 2019, and also this year presented talk in Linux Tech Days, and also published some of the blog and articles in public. So if you are interested, please follow this link. Then next, what is tinyML? Historically, IoT came first, and people don't know how to deal with huge amount of raw data. Then machine learning came in to deal with, to process that of a huge amount of data on cloud with big GPU. This is happening right now. Then in the future, what is needed is we have to be more nimble, enabled by tinyML to process data in place. So original definition of tinyML is running machine learning inference on ultra low power microcontroller. But from system software perspective, what matters is, as you see here, there are three technological areas: Linux, machine learning, constrained IoT. Overlapping of IoT and Linux is embedded Linux. Overlapping of Linux and machine learning. This is the place, cloud. Machine learning has been happening, and now it's moving towards edge computing. But there is a one missing part. IoT and machine learning, but Linux cannot fit in. This is the tinyML. That's why this has been untouched so far. And another aspect is machine learning compiler. As you have known, machine learning framework used to be incompatible. There is no compatibility. But the introduction of ONNX, Open Neural Network Exchange format, then now they have the compatibility. But this has solved only one aspect. Another aspect is the hardware diversity. And the top blue ones are machine learning frameworks, and the bottom pink ones are hardware, different hardware. To solve this, we need the machine learning compiler, and this is the figure taken from the TVM stack. And why local machine learning execution is important? There are many benefits: privacy, bandwidth, reliability, latency, and power consumption. But I will skip this today, this time. So, what is tinyML as a service? This is our approach towards the emerging tinyML technology as connectivity supplier. So the problems are, there are huge gaps between web and embedded. On the web, it's x86 or ARM64 with gigabyte of memory and terabyte of storage, and Linux is used with container virtualization. While embedded side, there are a variety of microcontrollers and variety of real-time operating systems with at most half megabyte of RAM, SRAM, and with a few megabytes of flash memory. And the variety of, there is no virtualization like Linux container at all. And also historically, machine learning has been developed on the cloud with big GPU. So the environment is too big to fit in the embedded environment. And also it's really hard to find an engineer who has both competence, machine learning and embedded. And if we consider about the characteristic of IoT is diverse. So we need some kind of customization service, like Pizza Online. You need to specify each of the preference one by one. So what it actually does, so there are 7 steps. Collect the device info, find the machine learning model, and squash machine learning model smaller size with a customized specialized runtime, because general purpose runtime is too big. And build the image per environment, like real-time operating system. And finally, the image has to be deployed onto devices. And this is the block diagram of tinyML as a service. So tinyML as a service located between the cloud and embedded. They are totally different worlds. And at first, it will taking the information from a device. And based on that information, appropriate pre-trained model can be downloaded onto tinyML as a service. Then to find out the appropriate machine learning compiler. And usually machine learning compiler is specialized per AI chip. So we cannot support all of the AI chips because there are hundreds of AI startups and big semiconductors are competing competing to dominate or to take the market share of machine learning inference. So we cannot support, or any single company cannot support all of the AI chips. And finally, machine learning compiler generates image, and then it generates OS image. It doesn't have to be OS image, but some module image has to be installed onto devices. So this is a little bit more fine-tuned block diagram. So we have the API server in front that's called the REST API to command what to do. And usually the backend partner, third party, will provide the OS builder and the machine learning compiler. It's stored in a Docker Hub. It can be called on demand. And we need some kind of lightweight protocol to orchestrate the machine learning inference on devices. And this time, we just pick up the lightweight OMA, lightweight M2M protocol. This is the quite lightweight. This is the IoT, one of the standard IoT protocols, which has a SOTA and FOTA. And FOTA and SOTA is a firmware over-the-air update and software over-the-air update. So the difference is SOTA is a partial update and FOTA is a full update. Of course, SOTA is more preferred. It is partial, so which means that we can save the network bandwidth. And this is the interface of the API server. Of course, we can make some kind of GUI front end, but so far we are just calling the REST API to execute. And this has the inference, and the target object can be inference, device, installer, and compiler. And device is the target, and the device is going to be associated with compiler, inference, and the installer. Then, if we call the patch or post command, then it will execute the rest of the processing. And another aspect is tinyML as a service will not change the data path. So, which means that, but it will change the data content. It used to be a raw data, but it could be more abstracted one by the power of machine learning. So, which means that if customer may already have the IoT platform, but the tinyML as a service can be optionally integrated onto any existing platform easily. And also the machine learning compiler is expected to be provided by the third party, which means that AI chip vendor. So this is the tinyML service. Then next, what is needed is the ecosystem. Why ecosystem matters? So as I said, any one company cannot support all of the components, but we need to collaborate anyway with other companies. To collaborate easily, what is needed is a standard interface. So now I specified three major interfaces. So one is machine learning compiler plugin interface. Then next, orchestration protocol, and third one is inference module format. I'm going to look at the one by one more details. So compiler plugin. The model is downloaded, pre-trained model is downloaded from the model zoo, and it's going to be pre-processed. It's going to be processed by machine learning compiler. But we want to support as many machine learning compilers as possible. So which means that this plugin interface needs to be standardized. So if we look at more details, that could be this kind of parameter, input and output, and it's going to be the available RAM size and ROM size and hardware and what kind of how much quantization and model and type. The next orchestration protocol. The generator module is going to be installed onto the device. It could be a partial or full update. Of course, we prefer partial updates. And this protocol doesn't have to be lightweight M2M protocol, but we picked up this because of the SOTA and FOTA, and also it has its standard way to expose device feature Queexo model. But it could be done with other lightweight protocol as well. But one requirement is over-the-air update. This is needed. The last one is inference module format. So as I said, diversity is characteristic of IoT. But if this module format is standardized, then we could say recompilation in some cases. So look at this picture. So I assume there are three profiles. So the top one is a general purpose environment. So in general purpose, you don't care much about the resources. So you can take just Onyx and run it on Onyx runtime. And the bottom one is bare metal. So there's no way to do anything smarter. So you only choice is the full update SOTA. But in the middle one, in the embedded profile, then you can do partial update to save the bandwidth and more safer, more energy efficient way to do the update. So those are the three interfaces, I think, to be agreed with the many stakeholders. If we look at the whole picture here, the interface or parameter could be like this. But as I said, single company cannot to define those kind of interfaces. So we really want to work with as many companies as possible to do that. And there are a little bit more faster steps about the composable machine learning. So there is no silver bullet. So the things to be processed by the big GPU cannot fit in the microcontroller. So we need to we can decompose and to be cascaded to be processed. In that case, we need to think about more interfaces. But I will skip this here. So that's why ecosystem matters, and we really want to collaborate with the vendors. And at last, I think I don't have much time, so I'll just quickly go through. So this is a simple POC because we cannot use our internal products. So this is the quite POC, and for the IoT system, I picked up the Elasticsearch, and Elasticsearch ELK stack is we assume this as a IoT system, and we use the lightweight M2M as a protocol to orchestrate. And for the device, we picked up the Nordic Semiconductor CG91. This has this kind of specs. And here is a use case diagram. So Elasticsearch resides as a IoT system, and the Keyban as a visualization place. So tinyML as a sub will communicate with lightweight M2 server, lightweight M2M server to get the info and to orchestrate for the model installation. So these are the steps to do: observe and collect the data, observe the normal lightweight M2 and collect the data and train the model with collected data and compile the model. And here is the sequence diagram. At first, by REST API interface, we will register inference, which inference to register inference, and register compiler, register installer, and to associate with each of the entities to the device. And then we execute the patch command. Then it will generate, at first, it will downloading the specified Onyx model, and it passes to the compiler. And after that, it's going to inquire some of the characteristics via lightweight M2 server. And this is a server, management server between the device and tinyML. And then after getting, based on that information, model is going to be generated, and the generated model is passed to the installer. And the installer will wrap that model into OS image, and it's going to be installed to the device via lightweight M2M total. And the result is going back to the return. This is how the feature. So let's show some of the videos. Okay, so okay, we have some time. So at first, you may want to see how the lesson. Lesson is one of the implementation of. Go back. So this has the predefined. This is one of the implementation. It has once device booting up, it's gonna be registered in this server. And if we click this, then it has the many predefined IPS objects. And the firmware update is also the one of the characteristics. So you don't have to implement anything, but it can be we just use that one. And for example, this is the accelerator, and each of the values can be observable. Then next is okay, so okay, so all the necessary components is in the Dockerize. So if we start tinyML as a service, then I just call the Docker compose here, just for the convenience. Then it's starting. There are several instances, and the content is like this. Yeah. So it's a API server and model is, and it's a gateway, a lightweight MSM, and also it requires the co-op server. Co-op is the protocol to be used for downloading the image. So then, okay, how much time? Okay, then, okay, now this is the calling the REST API, and we have the API server like this. This is a API server interface we call it from GUI, but it is a bit too much, so I'm using this GUI. So now it's calling the from here. It's now registered the compiler and the installer. Then model is registered. After that, it's gonna be calling the patch command. Then the model is downloaded onto the device, and it's starting. So once compilation is done, then next now it's flashing start using the lightweight M2 and so on. As you see here on the firmware entry, it has where to download the devices, and this is the console, left side is console of the device. It's flashing one by one, and once it's been installed, so now it's now 98%, 99%, it's gonna be rebooting. Yeah, now it's rebooted. And finally, it's gonna be showing up again here. Okay, and after that, so now it has the gesture detection is installed in the device. So on the left side is the accelerometer body. Then as you see here in the sensor unit, this is showing the 4 types of different gestures. And if this is unclear, it's going to be failed. But if you the correct movement, then it can be recognized from 0 to 3 values. And this is just a demo. And that's it. And at last, so we are looking for, this is just how can I say, tinyML as a service. And we really want to collaborate with AI chip vendor and machine learning compiler vendors. Thank you for listening.
Okay, thank you, Hiroshi. It was an interesting talk. I am monitoring question and answer streams. And by the way, while we take the questions, please take a quick poll on the talk. So there are a few interesting questions, Hiroshi. In the interest of time, we'll take just one question here. It says, what is model zoo in your talk? And
okay.
Yeah, to me, it reminds me of something like in Queexo AutoML, there is a selection box where you can basically select from different available machine learning models. Is Model Zoo doing something similar?
No, nothing special. It's just a location of the or archive of the different pre-trained models.
Okay.
With attributes.
Okay. So there are some other questions also, but when I combine this into one, it seems like there is a general question of like, where do we select that which model we want to build, which machine learning model we want to build? Is it being recommended automatically by this platform, or user has a choice?
So far, it's manually selected. But if we implement or specify the attribute in a standard way, then it could be selected automatically. That's the final goal. But I'm not at that stage because we need to consider many things to be what is the commonality of those kinds of things.
Okay, excellent. One more quick question is basically that how can we encrypt these models? How can we protect the IPs of the tinyML models which we are deploying on the edge? Is in this framework, is there a possibility of encryption?
Not right now, but internally we have a discussion about that and how to protect that with hardware security mechanism, which is the latest CPU has. But it's not implemented in this framework yet.
Okay, excellent. Okay, yeah, the ecosystem concept you presented was also very interesting. Thanks for that.
Yeah, I really
right.
want to collaborate with you guys. And,
yeah. No, that is really an important point, and I'm glad that you brought up that point here. So I would like to thank once again our sponsors. And again, as a reminder, this is the schedule for our next tinyML talks. We have Michael Gilda from Ant Micro and Stuart Pfeffer from Reality AI presenting different topics related to tinyML. And for any interest in presenting in tinyML talk series, please send an email to talks@tinyml.